In this video, we are going to study about the modular arithmetic, and so we are going to start modular arithmetic. Modular. Let A, B, B, we have some properties. Let A, B, C are integers and M is positive integer. M is positive integer. First property, A and A are congruence modulo M. Proof: A minus A equal to 0 and 0 is, and M divides 0. Here M divides A means it denotes M divides A. So M divides 0, since 0 can be written as M into 0 and 0 is integer. Therefore M divides, therefore M divides A minus A, and this implies A congruent to A modulo M. Again, second property, property 2. If A and B are congruent to modulo M, then B and A are congruent to modulo M. Proof: A B mod M implies M divides A minus B. Then by division algorithm, there exists Q in integers. There exists Q A integers such that A minus B equal to MQ, and we can write it as B minus A equal to M minus Q, and minus Q is in Z. Therefore B M divides B minus A, and B is congruence modulo A mod M. This is proved. Again, we have third property. Third property is if A is congruent to B modulo M and B is congruent to modulo C mod M, then A is congruent to C modulo M. Proof. A congruent to B modulo M implies M divides A minus B. Therefore, Q in integers such that A minus B equal to MQ and B, and similarly, if B is congruent to modulo C mod M, this implies M divides B minus C, and there exists Q dash in integers such that B minus C equal to MQ dash. Therefore, A minus B plus B minus C equal to MQ plus MQ dash, and Q plus Q dash can be read Q, since Q and Q dash are integers, therefore Q plus Q dash is also integers. Therefore, and A minus C equal to A minus B, B plus C, B minus C, B minus B and B are cancelled, and this MK where K equal to Q plus Q dash is also an integers. This implies M divides A minus C, and this is equivalent to A is congruent to C modulo M. This is proved. Third property has been proved here. Again, we are going to prove fourth property. If A is congruent to B modulo M, and then A plus C is congruent to B plus C modulo M. Since A is congruent to B modulo M, this implies M divides A minus B. Therefore, there exists Q and integers such that A minus B equal to MQ, and this can be written as A plus C, and we have added some extra, so therefore we subtract this to get same, and A plus C, and we can take it, write it as here MQ. This implies M divides A plus C minus B plus C, and this is equal to M plus C is congruent to B plus C modulo M. Thus, this property has been proved. Again, we are going to prove property fifth property is if A is congruent to B modulo M, then AC is congruent to modulo BC modulo M. We write its proof here. The proof is as follows. If A is congruent to B modulo M is given, implies M divides A minus B. Therefore, there exists Q and integers such that A minus B equal to MQ, and we can multiply both sides. An extra number C is C, where MQ and C, and A minus B AC minus BC, and this MQC. K equal to QC is also an integers. Therefore, this can be written as AC minus BC equal to MK, and K is integer. Therefore, M divides AC minus BC, and this is equivalent to AC is congruent to BC modulo M, and this is thus this theorem is, this property is proved. We have sixth property, which is a very important property, and we can property 6. If A is congruent to B modulo M, then A raised to power n is congruent to B raised to power n modulo M, or some n is positive integer, where n is positive integer. So, since we have given proof, is, since A is congruent to B modulo M, this implies M divides A minus B, and this implies A minus B equal to MQ, some Q in Z, Q is integer. By the definition, A equal to B plus MQ. This can be written as, we raise both sides power n, and we expand this by binomial theorem. Binomial theorem is, we can write it as, by binomial theorem as, B raised to power n, nc1, b n minus 1, mq, and similarly we can write last term ncn m q raised to power n, and this is the last term, and we can write it as a raised to power n equal to b raised to power n plus m into nc1 b n minus 1 q plus, and last term ncn m n minus m raised to power n minus 1. Since we have taken common m, and this is the multiple of m, and this number is also belongs to some integers, and this is also some integers, because every term is a integer. Therefore, we can write it as, we can take it as k, and k is some integers. Therefore, we can write as an equal to b raised to power n plus mk, where k is also an integer. Therefore, an minus bn equal to some integral product of m, and therefore m divides a raised to power n minus b raised to power n, and this can be written as an is congruent to b raised to power n mod m. And this theorem has been proved. Now, again, we are going to prove a last property, last and important property. Property number 7 is that if A is congruent to modulo B mod M, and fxb polynomials with integers coefficients, then fa is congruent to fb modulo m. We prove it. Since fx is a, let fx equal to C0 plus C1x plus C2x square plus C1x raised to power n be a polynomials. And fa minus fb can be written as C1 a minus b plus C2 a square minus b square and cn a raised to power n minus b raised to power n. And this can be written as fa minus fb equal to C1 a minus b C1 plus C2 a plus b plus Cn we replace we write seventh eighth property. Let A is congruent to modulo b, A is congruent to b modulo m, and fx be a polynomial with integer coefficients. Then fa is congruent to fb mod m. Since A is congruent to b mod m implies m divides a minus b, m divides a square minus b square, m divides a raised to power 3 minus b, and m divides a n minus b raised to power. Again, fx can be written as c0 plus c1x plus c2x square plus ck xk, where k is an integer, k is a positive integer since f is a polynomial. Therefore, we can write as fb minus fa equal to c1 to b minus a plus c2 b minus b square minus a square and ck bk minus ak. Since m divides b minus a, this implies by property 7, this is the property 6 7, m divides b minus a, therefore b minus a equal to mk1, b square minus a square equal to mk2. Similarly, bk minus ak equal to mk k, and this fb minus fa equal to mk1 c1 plus k2 c2 plus ck kk. Since c1 c2 and ck are the integers, therefore m into n fb minus fa, and m into p, and p is in also some integers. This implies that m divides fb minus fa, and therefore since m divides since fb minus fa equal to m into some integer, p is an integer, since we have shown that c1 c2 ck are the integers, k1 k2 and kk are the integers. Therefore, k1c1 plus k2c2 dot plus and so on plus ck is also an integer. So therefore, this can be taken equal to p, which is an integer, and thus we have written fp minus fa as a product of a positive integer m. Therefore, m divides fb minus fa, and this can be written as fa is congruent to fb modulo m. fb is congruent to modulo m. This is an important property, and we have taken it as last property, and we have proved that if a is congruent to modulo b, if a is congruent to b modulo m and fx be polynomials with integer coefficients, then fa is congruent to fb modulo m. Thus, we have proved all the property, and we are going to stop here, and again we will meet soon with new concepts. Thank you.